Enthalpy. Enthalpy is a funny word, isn't it? We're going to talk about energy. I know we're all kind of energy deficient right now. But we'll talk about energy. Maybe it'll give us some energy. Reactions can be exothermic, exit, thermo, referring to thermal energy. Thermal energy is given off. They release energy into the surroundings. Or they can be endothermic. Endo is like in. The energy is going into the reaction. They absorb energy from their surroundings. You probably have people like that in your life, right? They drain the energy out of you, right? And that's a real endothermic person. And then there are other people and you're around them and you're just energized because you're being endothermic and you're absorbing energy from them. The amount of thermal energy that's emitted or absorbed by a chemical reaction, and this would be under conditions of constant pressure. That's one of those details we have to throw in. Most reactions do occur under constant pressure. We call that enthalpy. So enthalpy is the thermal energy given off or absorbed by a chemical reaction at constant pressure. And we give this the symbol delta H. And you may wonder, why don't we call it delta E? Because enthalpy starts with E, and that's an H. Well, the enthalpy is, for the purposes of this class, you can think of it as being very similar to heat, and heat starts with H, so if that makes you feel better. AHrxn is a chemist's abbreviation for reaction, and so this is the change in heat of the reaction. So it's the amount of energy that's either coming in or going out. The sign of delta H is important because energy can come in or go out. It's just like money. In your checking account, if you actually have a register and you balance your checking account, you have to take the things coming in are positive, right? And the things going out are negative. You subtract them from your total. It's the same money, it's just which direction is it going is important. Well, the direction that the energy is going is important as well. And it follows the same pattern as money into your wallet. Energy coming in is positive, energy going out is negative. Money coming into your possession is a positive thing, right? Money going out is negative. We don't like to give money away or have to pay for stuff. It'd be nice if we didn't have to do that. Okay? So when we have an exothermic reaction, energy is released. And so we can draw these little energy diagrams. So here is the reactants. These are the reactants. And they are higher in energy than the products. And we've talked about conservation of energy, right? Energy can't just appear or disappear. It can flow from one thing to another. It can be transformed, but it can't just disappear. So the reactants are higher in energy, the products are lower. They got lower because energy came out. So energy came out and the energy is released. We say that the heat of reaction or the enthalpy of the reaction is negative. This went down. The overall energy of this system went down. That's a negative change in energy. In an endothermic reaction, the reactants start out at low energy, and then they absorb energy, endothermic energy coming in, and the products then have a higher energy. And so this delta H is positive because the energy is coming in. We will most often encounter delta H like this. So here is the combustion of methane, which is the main component of natural gas. So methane reacts with oxygen. That's what happens in a combustion reaction. Forms carbon dioxide and water. And when methane burns, that's what we've been doing when we light our Bunsen burners. Is that exothermic or endothermic? Exothermic, right? Because it gets hot, right? You stick your hand there, you're going to burn your hand. There's a lot of heat given off by that chemical reaction of the combustion of methane. So here, delta H is negative. because it's always from the point of view of the reaction. Just like money going in and out. Let's say I owed my son Zach some money because he would buy stuff and then I have to reimburse him. So from his point of view, when I wrote him that check, that was a positive thing for him. For me, it was a negative thing, the money leaving, right? And so we just need to keep that direction straight. So here the energy is leaving and we're thinking about the reaction, not the surroundings. The magnitude of this tells us that 802.3 kilojoules of heat are emitted when this reaction is interpreted in terms of moles. So 1 mole of methane making 2 moles of oxygen, reacting with 2 moles of oxygen, making 1 mole of CO2 and 2 moles of water. This is the amount of energy that's released. For positive delta H's, that means it's an endothermic reaction. When nitrogen and oxygen react to form nitrogen monoxide, it absorbs energy from the surroundings. And so it's a positive delta H. 182.6 kilojoules of energy for 1 mole of this and 1 mole of that reacting to form 2 moles of that. Because if you had 4 moles of nitrogen instead of 2, if you had 4 moles instead of 1, good grief, 4 moles instead of 1, then more energy would have to come in, right? The amount of energy released depends on the amount of stuff that reacts. And so this number has to be related to the quantities in the reactions. And so we've chosen to use the number of moles from the balanced chemical equation. So we can use delta H and do stoichiometry type calculations. Like I just said, the amount of heat absorbed or emitted depends on the amounts of reactants that actually are reacting. And so we usually specify it in terms of that balanced chemical equation for the stoichiometric amounts of reactants and products as written. Occasionally you'll see one that's not with its lowest coefficients, or you might see one with fractional coefficients. However they're written, you use it as written. And the magnitude tells us how much is transferred. The sign tells us what direction it's going, and it's for the molar amounts. Not for the masses, it's for the moles. So if we look at this one, this is a combustion of propane. So we've got this hydrocarbon, it's got carbon and hydrogen, reacting with oxygen, forming CO2 and water. Delta H of the reaction is minus 2,044 kilojoules. So the negative sign tells us this is exothermic, it's giving off heat. We're going to get 2,044 kilojoules for 1 mole of this. Those ratios can be used to make conversion factors. So, oops, wrong place. I got lost. So we can make a conversion factor like this. We can say there's 2,044 kilojoules for every 1 mole of propane. So this is like an extension of this chemical equation, and we just learned how to do moles of this to moles of that, or moles of this to moles of this, right? So we take this number and we can relate it to any of these in terms of moles and that number, the coefficient. Does that make sense? So I could make a relationship between moles of oxygen, would be 5 moles of oxygen for every 2,044 kilojoules. So we're taking this and we're inserting mole as the unit. And we've got this guy and this guy. And we put one on top and we put one on the bottom. And which one goes on top or bottom depends on how it works out for the units in the equation. Any questions? Let's do an example. Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Well, let's take our equation and use it to organize this number here. 155 grams of ammonia. So I'm going to write 155 grams under ammonia, because that's what it relates to. Calculate the heat in kilojoules. Well, remember I said enthalpy, delta H, is like heat, and here we see kilojoules. So that's our question, how many kilojoules? You can kind of treat this as part of the, well, it is part of the equation. The delta H here would be given, yes. They could make you look it up in a table. It's not anything that you would memorize or be able to just figure out. No, no. So what was our chant for stoichiometry? Grams to moles to moles to grams. You guys aren't really into chants, are you? Sometimes I can get the whole class to chant with me. Grams to moles to moles to grams. Of course, it's not usually the afternoon class. It's usually the morning class. So that's our normal thing. Are we going to do just that plain old normal thing for this problem? Is it asking us to find grams of something? No. We're going to have to twist it up a little bit. We're going to have an alternate ending to our path. We're going to take a little detour at the end. They're asking us to find kilojoules. Calculate the heat in kilojoules. We have a relationship here between kilojoules and moles of each of these things, right? So this is kind of our thinking. Let's flesh it out a little bit. The thing we're starting with is grams of ammonia. So I'm still working on the path here. Grams of ammonia. I can convert that to what? Moles of ammonia, right? Now normally we go to moles of something else. Do we have to do that here? No, we don't, because we know that there are 4 moles of ammonia for every 906 kilojoules of energy. And if we were going to convert to another thing in moles, which one would it be? They don't mention one. We don't need to go there, so we can actually take a little shortcut here and go directly to kilojoules. So these problems end up being a little bit shorter. Any questions about the path? The path is the critical part, and that's what's a little different here. So then we've got 155 grams of ammonia times, we're going to go to moles of ammonia, and then we're going to go to kilojoules. Following the same pattern of dimensional analysis, we're going to put grams of ammonia down there so they cancel out, and moles of ammonia down here so they cancel out. This is the part that comes from the equation now, 906 kilojoules. The sign tells us which direction the energy is going. Okay, so we don't need to put the minus sign in here, although you can. And then this guy, that's the molar mass of ammonia, which we calculated earlier. Yeah, 17. Good grief. I knew that too. 17. So there we go. 155 divided by 17.034. times 906. So 8244.1 kilojoules. How many sig figs? 3. So the best thing is to call that 8.24 times 10 to the third kilojoules. Now, whether you include the sign or not is unfortunately quite confusing. If it says calculate the heat released, the word released is telling us the direction. If it says heat given off or heat absorbed, that's going to be telling you the direction, and so then you don't necessarily need the sign. And so just pay very attention to how Mastering Chemistry asks the question. I will not try to trick you with the sign on an exam. Any questions? This is another type of question. This is backwards of the other one. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? What mass of CO2 is produced? Like I said, we're a little bit tired today. I don't think we need to do that part. How's that? Well, we've got a number here, 1.5 times 10 to the third kilojoules. Well, I'm going to write that over here under this thing that has kilojoules. 1.5 times 10 to the third. What mass of butane in grams? We haven't learned how to write the formula for butane, but this is oxygen, that's carbon dioxide, that's water, so the other one must be butane. Let's see if I can find it. So question mark, grams. Yes, there's a fraction in here. It's okay. Just leave it alone. When we're dealing with energy, this number is appropriate for this equation as written. Okay? So our normal path was grams to moles to moles to grams. Grams to moles to grams. This time we are trying to find grams. So we are going to end up here, but we're starting with kilojoules instead. And what we learned in the previous example is we don't have to do a mole-to-mole thing with the kilojoules because this relates directly to any of these. And so we don't have to go moles of butane to moles of CO2 and then to this. We can just go directly from moles of butane to kilojoules or vice versa. And so our path is actually going to start right here. It's like, I don't know, maybe one of the condors from Diego came and picked Dora up and gave her a ride halfway, right, and set her down here. So she doesn't actually have to do this part. She can start here and just go directly moles to grams. Did you guys ever watch Diego? Go, Diego, go. And then there was a kid on my son's baseball team named Diego. Go, Diego, go! It's just, yeah, I just doesn't, I don't know. Awesome kid, great baseball player. So we're going to start here with the kilojoules, 1.5 times 10 to the third kilojoules. And we're going to convert that to moles of the thing that we're interested in. C4H10. I don't want grams down there. I'm jumping ahead of myself anyway. And then we want to get to grams of C4H10. That's our path. Kilojoules to moles to grams. Kilojoules to moles to grams. And previous unit down in the bottom. So those cancel. And do it again over here. And this cancels. The relationship between moles and kilojoules comes from the balanced chemical equation. We find C4H10, and there's a 4 in front of it. That means 4 moles of that. So 4 moles of that. 4 moles of that will generate this amount of energy. 2658 kilojoules. Grams to moles is the molar mass. That's where you look at the periodic table and the chemical formula. We've got 4 times the mass of carbon plus 10 times the mass of hydrogen. 4 times 12.01 plus 10 times 1.008 equals 58.12. That tells us that 1 mole of C4H10 weighs 58.12 grams. Now we just plug and chug. 1.5 EE3 times 4 divided by 2658 times 58.12 equals. And this is giving me 131.196 grams. How many sig figs? 2. Our starting number had 2 significant figures. This had 4, that had 4. These guys are exact. So 2, we need to be careful here. Let's put it in scientific notation. 1.3 times 10 to the 2 grams of butane. Any questions? This is a variation on stoichiometry. We will encounter a couple of other variations on stoichiometry. Ah, yes, the sign. Often in the homework, meaning mastering chemistry, the absolute value of Q, which, this is one of those sets of slides that I ran out of time and didn't edit very well. Q is heat. Don't ask me why. When they're saying calculate the amount of heat, it's actually Q. They're really wanting the absolute value, and words are used to convey the sign, whether it's being absorbed or given off. Okay? Bunsen burners is the what we're doing when we light the Bunsen burner is we're burning the methane in the natural gas. You also need oxygen to burn it, and the Bunsen burners have a little valve. We've learned how to adjust them, and that allows you to adjust the amount of oxygen. And if you have that completely closed off, I showed you it looks like a candle, and if you get too much oxygen, you can actually cause the flame to get cooler again and even extinguish it. And so here's pictures of the Bunsen burner with various amounts of air. So this is no air. If you wanted to generate light because the power was out, that would be your best bet. That's going to give off the most light, but that's not going to give off much heat, and it's going to be a sooty flame. It's going to deposit carbon all over your glassware. As we get a little more air, we start to see a blue flame forming. This is what you want your flame to look like. It's got a nice inner blue cone, and it's going to have a gentle roar. It's going to make some sound. If you give it too much air, that's where you get this flame that looks like it's floating. And this flame will blow out easily, and you never want your Bunsen burner to be just releasing gas into the air. This flame will not be as hot as this one. Here's your optimum flame right there. And there's chapter 8 in review.